So the next thing we're going to talk about that pretty heavily relies on standard deviation, we're going to talk about the normal distribution. So in this particular textbook, this is not covered very heavily, so I actually imported some sources from other textbooks in on your homework. Now, it's not going to mean anything to you because your homework's going to look just like it normally does. But just know that's why I'm not giving you a section number, because normal distribution is kind of very quickly covered in this book. So from last class, recall that histograms are kind of like a bar graph. And so let's draw a histogram, and I don't want you to be really, really detailed. So let's draw a histogram where it just looks like kind of the bars are different heights. I don't really care about it having any sort of pattern. So yours doesn't need to look just like mine. Just try to like vary the list a little bit, or vary the height of the bars. And so a lot of times when we collect data, we'll show it in a histogram like this. But what we do with it a lot is we draw curves to kind of estimate the heights of the bars. So curves can be drawn to sort of approximate the data shown in a histogram. And so a lot of times when you see line graphs, they're actually based from histograms. And so what I mean by that is you might have a curve that kind of does this and kind of tries to hit all the peaks and valleys of what we have here. Okay. So in other words, you would kind of take out the bars and you might be left with just the line graph, and the line graph would still show the peaks and the valleys, right? How the graph was increasing and where it was decreasing and so on and so forth. So I think it's pretty clear. The one that I just showed you, the data doesn't really seem to have a pattern. So the data can be distributed very differently. So here is one type of data presentation we can have. Left skewed means that the data has a left tail. So if you had a curve, it might look something like this, like there's a tail to the left and then the values to the right kind of peak. Okay, so notice in a left tail situation, most values are clustered at the right. So skewing indicates where the tail is, not where the peak is. So it's a little bit maybe backwards from what you might think. So right skewed is going to mean that the data obviously has a right tail. So it might look like this. The peak would be over here, and then it would kind of trail off to the right. Okay. Notice here most of the values are on the left. But what we're going to spend some time looking at for the rest of the period today is data that looks symmetric or near symmetric, because we can actually make some conclusions about symmetric data that we can't necessarily when it looks skewed one way or the other. Symmetric data peaks in the center. And is the same on either side. So it is a curve that looks kind of like this, where it goes out in the center and then gets less and less likely as we go out. Remember, we had a name for this last class. Do you remember what we called this? We called it bell-shaped, right? And so what we're going to be discussing is data that looks like this shape. A normal distribution. So I'm going to underline this. A normal distribution describes data with a single mode, in other words, a single peak, a single mode in the center. So we can have bimodal, but when there's one mode, it's called unimodal. You know, the prefix uni means one, kind of like a unicycle has one wheel, right? So if it's unimodal or one modal, it'll also be symmetric, and it will be bell-shaped. So this is essentially what a normal distribution looks like, both in histogram form and in curve form. So in histogram form, it looks like we're peaking in the center, so maybe start in the center and draw one of your bars taller than the other, and then we kind of go from there. So the curve would kind of look like this, right? If you were to draw the curve, it would kind of look like it's peaking in the center, right, and kind of going off as we go. So this is called a bell curve. We talked about it last time, I think. But this would be approximately a normal distribution. A true normal distribution is actually perfect on both sides, and I probably didn't draw it perfectly. But when data is a normal distribution or a bell-shaped curve like this, it's actually very predictable. Okay? So it's very easy to kind of predict what the values will be. So many things in real life can follow or traditionally do follow a normal distribution. Some things that are some examples. The height of people. Now you do have to usually split the people up by gender and often actually by nationality also, okay? Because like American men are usually a different average height than, say, Asian men, okay? So sometimes you have to split it up like that. But in general, measurements like shoe size or height are usually a normal distribution. So to put it in easier terms, I think the average woman's shoe size in America is about an 8, okay? So there's lots of women that have about an 8 shoe size, and then 7 and 9 are still pretty likely, but not as likely, okay? But then the further you get away from 8, like there's way less 6s and 10s, and then not very many 5s and 11s. Do you see what I mean? So like the further you go out from that shoe size of 8, the less women there will be. So the size 8 would be here, and then we would taper off the further we get away from 8, right? So very few people have like really small shoe sizes or really big shoe sizes. But sizes of products produced on machines will also follow a normal distribution. Although with the accuracy of production, usually it's like fractions of even a millimeter sometimes. It's usually very, very small. Errors of measurement also follow a normal distribution often. Okay, even the best programmed machine will have errors, okay? And so the errors usually follow a normal distribution. Other things are like blood pressure and other health measurements. So how your doctor decides whether you have concerning numbers is there's an average, right? And the further you get away from the average, the less and less likely that is. And then I'm just going to say this, sometimes grades on exams/assignments can follow a normal distribution. So there aren't very many teachers that do this anymore, but there are some teachers that grade on a bell curve, okay? In other words, they come up with what they think the most common grade is, and that becomes the average, okay? And then the further you go out from that average, the less and less likely it is. For instance, when I was a freshman many years ago, we won't go into how many, but I had a calculus teacher who the average of his tests was extremely low. Like, he prided himself in giving difficult tests. So as a freshman, I got my first test back and I had like a 34, or no, I didn't have a 30, I think I had like 42 or something. And I like panicked thinking I failed. But actually the average was a 30. So my 42 was actually an A. Don't know how, okay? But really, essentially what that tells you is that test was too difficult, right? If the average was 30, then it means, you know, that no one was getting a decent grade on the test. So what he did is he took the 30, and I'm just throwing numbers out there, it was something close to that. The 30 was the average, so he made 30s C's, and then anything less than that were D's and F's, and anything more than the 30, or, you know, some range of low 30s was a B or an A, okay? And I was high enough above the 30 to be considered an A, okay? It also could work negatively for you, which is why a lot of teachers don't grade on a bell curve anymore. In other words, if the common grade is actually in the 80s, then that would be your C. So that would probably make people angry, right? So the 80s would be your C, and then anything lower would be your D's and F's, and anything higher would be your A's and B's. So a lot of times you're not going to see that anymore, but just know that that used to be a thing. So here's some examples of what the curves might look like. Just to make sure that we kind of understand. So let's say you have kind of a number line, and then you have data that kind of peaks and goes like this. In a true normal distribution, the mean and the median and the mode are all the same. In other words, the average falls in the middle, and the middle is the most likely outcome, right? Mode means the most frequent. And so a true normal distribution is perfectly symmetrical, which means that 50% of your data is to the left and 50% of your data is to the right. But just know that this is also a normal distribution. So a lot of times what we talk about is normal distributions that might not peak quite as much. But still, we would say that 50% is here and 50% is here. Okay, so this is still the mean equals the median equals the mode. So there's basically versions of a normal distribution, but as long as it's symmetric, as long as that peak is occurring in the center, then it is at least approximately normal. Okay, so comparing these two, the graph in Part B has the higher standard deviation. And the reason it has a higher standard deviation is because the values seem more spread out. The graph is wider. So the values are more spread out from the center. In other words, the graph is wider. Because in case we've forgotten, we just covered it, but recall that standard deviation measures how far away from the mean you are. All right, so whatever we don't finish today, we will pick back up on Friday. But this is only for a normal distribution. The following relationships are going to be true. And I kind of want you to draw this in kind of some detail. I want you to draw a line with a curve that looks kind of symmetric like I just did there. And so here we're going to list how many standard deviations we are away from the middle. So in the middle, we are 0 standard deviations away from the middle, right? We're square on the middle. But then if we go out, this is -1 standard deviation, and this is +1 standard deviation away from the middle. And then this is -2 standard deviations away from the middle and 2. And then -3 and 3. So when you have a normal standard deviation, if you only deviate out 1 standard deviation from the mean, you will actually keep 68% of the values. So I'm going to write that off to the side. So what this says is that about 68% of the values are within 1 standard deviation of the mean. Okay, this is only for bell-shaped data. All right, so skip some space and let's draw another one kind of just like it. It doesn't have to be perfect. It just needs to peak in the center and try to make it symmetrical. This one's not quite as good as the other one that I drew. So we're going to do the same kind of startup. We're going to be 0, 1, 2, and then 3. I don't know why I was making these negative, right? These are positives. So if we go out further and we take all the values that are within 2 standard deviations, we are going to cover 95% of them. Okay? In other words, we're going to cover a lot more ground. So about 95% of the values are actually within 2 standard deviations of the mean. So I'm going to kind of circle the significant information. 68% are within 1, 95% are within 2. And so let's do one more. Typically, we only go out 3 standard deviations. I think my pictures are getting worse as I go here. So I'm going to go ahead and label this horizontal axis 2. These represent how many standard deviations away we are. So if you can go out to 3 standard deviations, okay, notice that that is going to cover nearly everything, right? Like I'm going to draw it kind of like that so you can really see it. Notice the only thing left is like very little trace elements on both sides, and actually it covers 99.7. So some textbooks will say almost all instead of 99.7, okay? And so the statement here is about 99.7% of the values are within 3 standard deviations. And remember, this is all for the purpose of predicting data. We want to be able to predict data effectively. Okay, so next time we're going to look a little bit more at this.